get this started. Okay. So I didn't look through this chapter in your book, but do you remember the Bohr model of the atom? Did you look at that? There's the electrons orbiting the nucleus, but they only do so at specific distances. Actually, I think that's more important is this part. So you did like these. We have these numbers that represent the orbital, and then the orbital shell. Is this ringing any bells or no? Yeah? Okay. All right. So then when you look at the periodic table, down here, right? So for like helium, you can do 1 because it's in the first row of the periodic table, or at least you can find all of these things from the periodic table. So because helium is in the first row, we start at 1s. Hydrogen is 1s1. Helium is 1s2. So for every box that we move on the periodic table, for every element, we add one more electron. And then those electrons occupy different spaces around the nucleus. So for lithium, if we were to write out its electron configuration, then we have 1 electron for hydrogen, 1 electron for helium. So it's our 1, first row, s, and then 2 electrons. And then we move down to the second row. So that's 2s. So for every row that you go down, you're going to add another s orbital. But then since lithium's in the first box, it's only got 1 more electron. So it's 1s, or 2s1. And the reason this works out on the periodic table is because lithium also has 3 protons. So to be electrically neutral, each of those protons has a positive charge. So then 3 electrons would balance out the 3 protons and give it a charge of 0. And then what's important, well, this is important today because we're going to be looking at how valence electrons interact to bond. So for lithium, these 1s2 electrons are in a smaller orbital that's inside of this 2s1 orbital. So those 2s1, these outer electrons are the only ones that are going to interact. So when we get to Lewis structures for something like lithium, we only count the number of valence electrons. So for lithium, it would be a single valence electron. So then you can continue to fill these up. And so this example of carbon is going to be helpful for today. So carbon, again, we start at hydrogen. So that's 1s2 because we have hydrogen, helium. And we go back down to the second row. And so that's 2s now. And so we have lithium, beryllium, 2s2. And then we move over to what is called the p block. And that's where we start filling our p orbitals. So boron is 1 electron, carbon is 2 electrons. So then carbon ends up with a 2p2. So the 2 represents the row on the periodic table. And the superscript here represents how many electrons in that block that your element has. So for carbon here, because this is a 2s, and this is a 2p, those are both valence electrons. Both of those represent valence electrons. So carbon has a total of 4 valence electrons. We represent those with little dots around carbon. Yeah, 4th counting across. Okay. I don't think we're going to be doing electron orbital diagrams today, but it helps. I liked Mr. Guerrero's slides for this because your book is in a different order than the book that I'm using for my Chem 20. So You guys have already talked about that. I'm just talking about electron diagrams in Chem 20 this week. So we have these Lewis symbols. And so these are Lewis symbols are a convenient way to represent valence electrons, which are shown as dots placed on sides, top, or bottom of the symbols for the element. So we've got this table from your book, these different Lewis symbols. And again, we can look at this. They have actually conveniently arranged this like the periodic table. So right, top left, we have hydrogen. All the way on the right, we have helium. And those are the only ones that are kind of weird because they're both filling an s orbital. Then we can go down to lithium and beryllium. We see those on the left side. And then immediately following those on the periodic table, we have boron and carbon. And just like those sort of introductory examples, right, carbon has 4 valence electrons. And so, yeah, just remember that it's the number, and actually for neutral atoms, which we'll see whether that makes a difference later, for neutral atoms, you can use the column number to tell you how many valence electrons you have. So carbon is in 14, but these also have alternative names where you add an A at the end. So it excludes the D block, which is all these, I wish I had a laser pointer. So it's like titanium and scandium. 3 through 12 there in the middle, that's your transition metal block, also called the D block. So group 1 and 2 would be 1A, 2A. And we can also call 13 3A, and then 4A, 5A, 6A, 7A, 8A. And that's how many valence electrons those atoms have. And we'll primarily be staying above the D block. We won't have to worry about that. So we draw these out like this. All right, so for boron, it's only got 3 valence electrons. It's in 3A. Nitrogen has 5 electrons, valence electrons. So 3, 4, 5. Oxygen has 6. Fluorine has 7. Neon has 8. So you can even see this here that as we go across, oh yeah, it's on here. 1, 2, 3, 4, 5, 6, 7, 8. Also matches with these numbers that I've drawn here. Give it a second there. Again, if you're on the Zoom call, or one person on the Zoom call, feel free to type questions that you have in the chat, and we'll try and look over at those from time to time. Okay. So why do these electrons, why do atoms form bonds? And in part, it's because they want to be in a lower energy state. And one of the lowest energy states that they can be in is to have completed valence shells. Kind of think of atoms as collectors, and they want to have the full set of electrons for whatever energy level that they're at. So for hydrogen, right, each of these hydrogens, and hydrogen's again, kind of a weird exception. Hydrogen wants to be like helium. So it wants to have 2 electrons. Zoom in on this. So yeah, so as these guys come together to form a bond, they share their 2 electrons, or their collective 2 electrons. They each share an electron with each other, so that together they have 2 electrons. And so as these hydrogen atoms combine and form this H2, they're lowering their energy state by getting that full set. This is actually the reason why the Brinkelhoff compounds, so hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, it's why they form these diatomic molecules, because by combining together, they can get an oxygen combined with an oxygen, nitrogen with a nitrogen. They form these full sets of electrons. Other atoms can't do that. So like carbon, We draw carbon. We know that carbon has two, well, here, I'll do it this way. 2, 3, 4. 4. So even if they pool their electrons together, well, they'd have to form, we'll kind of get into this later. So we can represent bonds as lines, and each line represents 2 electrons. So they'd have to form, between the two of them, 4 bonds at the same time, which doesn't happen in nature, in order for them to both have a full set of 8 electrons. All right, so they're taking these electrons and they're sharing them. Maybe a better example would be something like boron. So if we have boron, boron only has 3 electrons, but everything wants to have, and so it doesn't really matter where you put the dots around. Everything wants to have 8 electrons. So between the 2 boron atoms, they don't have enough electrons to even share and get to 8. So they're not going to share. It's not going to put them into a lower energy state. You guys talked about covalent and ionic bonds? Yeah, okay. So this is why covalent bonds form. They're sharing the electrons versus ionic bonds where they're exchanging electrons. Yeah, they do get a full 1. Yeah, 2s, 2. You won't get 4 hydrogens bonding together. Yeah, because they only have 1 electron each, but you're right. Yeah, so if you had, and we covered this a little bit right at the beginning, but that's why, yeah, like lithium has 3 electrons. So the s orbitals can only hold 2 electrons each. So once the 1s is filled, then it moves up to the 2s orbital. So you'd have 1s2, 2s with a superscript 1, indicating how those are filled. Right, so, oh, here, perfect. Fluorine is another example of these diatomic elements coming together. So they each have 7. So they don't share all of their electrons. They only have to share a single electron with each other. And then they can form this bonding pair. And so that's a pair of electrons that's forming a bond between them, which we can also represent with a line. And that's why we get fluorine molecules that are F2. Because when they share this electron, we can, so we'll use a highlighter for this maybe. And count these. 1, oh, it's huge. A small highlighter. So that's too small. 1, 2, 3, 4, 5, 6. And then every bond represents 2 electrons. So they're sharing these. So it's 7 and 8. And then again, for this other one, we have 1, 2, 3, 4, 5, 6, 7, 8. So they are happy with 8 electrons, and that's why they form these bonds. And that's also a good segue into why we draw, or how we draw these Lewis structures. So for carbon with 4 hydrogens, when you have to draw these out yourself and like homework, usually the single atom is going to be your central atom, or I will tell you in like an exam question what the central atom is going to be. So for this one, we have carbon as our central atom. And we know, again, carbon has, right, up here, and on the periodic table, 4 valence electrons. So when carbon forms bonds with hydrogen, it forms 4 covalent bonds where it shares its electron with 1 electron with each of those hydrogens. Hydrogen's special, it only really wants 2. But then carbon gets a full set of 8. And then we can redraw these with those bonds as lines. And then we also have these space filling models here. And so you'll need to know how to draw Lewis structures and then also Lewis structures with lines as bonds. I'm not going to have you draw. This is not an art class. You're not going to have to draw 3D space-filled models. Any questions there? Yeah. They mean the same thing. Yeah, so if they're this close together, I think in general, you're gonna see them drawn as lines because then it distinguishes the bonds from those just valence electrons that are still around. So these ones are all with hydrogen, so that makes them a little simpler because you don't have so many valence electrons floating around. But these don't have to be hydrogen. Okay, so we got some practice here. I think one of the ways the strategy I would take when doing these is to write out all of the valence electrons of each of the elements that you have first. So if we have phosphorus trichloride, that is PCl3. Let's do phosphorus, chlorine, and it's very similar to sort of doing the molecular mass. The phosphorus, we check out phosphorus in the periodic table. It's in 5A. So it's got 5 valence electrons. And then chlorine is in 7A and has 7 valence electrons. Then for chlorine, kind of weird because the steps for doing this are later. So the first thing you want to do is figure out how many valence electrons you've got floating around per atom. So we've got 7 electrons for each chlorine, and we have 3 chlorine atoms. So we're going to multiply that by 3. And so then we'll do 5 plus 7 times 3. 5 plus 7 times 3 for a total of 26 electrons. And we'll distribute those as we draw the structure. So again, in this one, it doesn't tell us specifically what the central atom is, but you can assume that it's the single element. So since we only have 1 phosphorus, that'll be our central. And then we'll draw the chlorine atoms with single bonds around that central phosphorus. Okay, so that's used up because, right, we're being told that this is a molecule. So at the very least, our bare minimum is a single bond between each outer atom and the central atom. And don't worry about, like what if the chlorine bonds to another chlorine? We're not gonna have any rings in this class. It's just gonna be everything bound to a central atom. So you'll never see like another bond formed here to make a triangle or anything of that nature. That's stuff for organic chemistry. All right, so each of these bonds, bonds equal lines equal 2 electrons. So every bond that we form is going to be, what was that? So somebody doing a Halloween thing. Okay, so bonds equal lines equals 2 electrons. We'll see double bonds, maybe in this next one. Okay, so we've used these 3 bonds. Those are 2 electrons each, so it's 6 electrons that we've used up. So you can say from our 26, we're gonna subtract out those 6. So how do I wanna write this? Oh, we're gonna subtract out 6 electrons. Those are our bonding electrons. So we're gonna have 20 electrons then that we get to fill in around these. I generally fill in for the central atom first. So, right, everything's going to want to have 8 total electrons. And then each bond counts as 2 electrons for both atoms that it's connected to. So if we add 2 more free electrons to phosphorus, it now has 8 total electrons. And so it's going to be happy there. So now we've got 18 electrons left to work with. And when you're doing this on your own, and when I do these, I'll generally just count as I'm dotting them in, because you can just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this one worked out. That won't always be the case, but we'll see how to deal with that later on. I think one of the nice things about chemistry is that things are supposed to work out nicely. So this is drawn, this atom exists because of the way the electrons bond. So if this is a real molecule, then this Lewis structure should work out so that everything has 8 valence electrons. If it doesn't, that means you probably counted your number of valence electrons wrong in the first place, used the wrong valence electrons from the periodic table, or you've got too many electrons on one atom or another. Especially if you have electrons left over. Okay, so we'll look at this next one. Actually, first, are there any questions about that one? No? Anything in the chat? Doesn't look like it. Okay, so our next one, sodium chlorite, so a component of mouthwashes, toothpastes, and contact lens cleaning solutions. We're going to draw the Lewis structure for the chlorite ion, ClO2 minus. Now, minus is important because it tells us that we have 1 extra electron. So we'll start by writing out all of the atoms that we have. We're going to have chlorine, we're going to have oxygen, and then we're also going to include a section for any charges that we have. So I'm just going to write that as electrons here. So how many valence electrons does chlorine have? Yep, 7. What about oxygen? Be 6. And then this last one, or maybe I should put not E, but let's call this, I'm going to write out charge. And so because we have this charge, that's a negative charge, indicates 1 extra electron. Well, it's going to equal extra electrons in general. A positive charge equals, I guess, removed electrons. So if you have a positive charge on something, for every positive charge, so if you have a +1, you're going to subtract and remove 1 electron from your total valence electron pool. If you have a 2+ charge, then you'll subtract 2 electrons, so on and so forth. And the opposite for negative charges. Yeah. We don't have a charge for PCl3. No. I'm just using it as written here. For ClO2, we do see a minus charge as it's written there. Okay, so for our -1, then we're going to add 1 more electron. So again, chlorine, we only have 1 of those. We're going to multiply 6, or number of valence electrons from oxygen, by 2, and then add in that 1 extra electron. So we'll get 12, 19, 20 total valence electrons. And now, again, we assume that the single atom is our central atom. All right, chlorine. And then we're going to bond that to our oxygen atoms. So then we've used up 4 electrons for bonds. So I'm going to write -4. I'm going to change this one up here too to say bonded electrons. And actually for my Chem 20, I have a good worksheet for this. I'll make a note to share that with you guys. It won't be worth, unless you want me to make it worth some points, I can make it worth some points. Otherwise, it's just a lot of practice problems. I don't want to like heap more work onto you guys. The transition's difficult enough. Let me just make a note to do this. Share Lewis worksheet. Okay. All right, so now we've got our total number of electrons, 20 electrons, and then we've added our single bonds in, because at the very least, we're gonna have those single bonds. Also, if you're doing this in pen, I highly recommend doing it in pencil. You'll see why. And then we've subtracted those 4 bonded electrons out from our total valence electrons. So we're working now with 16 electrons that we're going to add in as our free electrons. I'm going to start with the central atom. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Move this over just a little bit. And then when we have a charged molecule, we surround it in brackets, and we put the charge on the outside of those brackets. Okay. Those are a couple examples. All right, if there's no questions, move on. So sometimes we'll have, like I mentioned, double or triple bonds. So you represent double bonds as a little equal sign, but it's 2 lines. So each line represents 2 electrons. So a double bond is 4 electrons. Triple bonds we represent with 3 lines. All right, so each line representing 1 bonded pair of electrons. So that's 6 electrons. It's 2 electrons, or sorry, 4 and 6 electrons. So these double and triple bonds are useful when we get to the step where we're dotting in all the electrons. If you run out of electrons, you can start to shuffle electrons around and make more bonds to compensate for those missing electrons. So for carbon dioxide, right, and here we're told the central atom is C. Thank you very much, Timberlake. We have carbon and oxygen, right? The 2 atoms that are making up our atom here. And from the periodic table, carbon has 4, and oxygen 6. Yep. Times 2. Yep. And if you want me to go faster, I can go faster. You got it though. Okay, all right. But you got it, yeah. So four electrons for carbon, 6 for oxygen. We multiply that by 2. We have a total of 16. So now we can go and write in our central atom, which here we're told, but again, you can assume that the single atom is going to be your central atom if it's not otherwise stated. And then we'll draw in our bonds for oxygen. So now we've done two bonds here. So for our initial counting, we're going to subtract out 4 bonded electrons. So we're left with 12 electrons to place. So if we just start putting these in, again, I like to start with the central atom. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've run out of electrons, but this is why we have double bonds, triple bonds. So in this case, we can take one of our electron pairs from here. Actually, maybe it would be good to say this too. When you're drawing these out, if you can try to even out your electrons so they're distributed around your outer atoms. So let me actually show you a way to do that. So instead of drawing these in here, let's just start over and say, again, fill up your central atom. So 1, 2, 3, 4. And then alternate between or around, just like if you're dealing cards, we're going to go around or back and forth between our outer atoms. So we've used up 1, 2, 3, 4. So we're just going to go 5, 6, 7, 8, 9, 10, 11, 12. So by divvying out those electrons that way, then you can even them out. No, I guess it is a structure of CO2. So if we've got, if we don't have enough electrons on our outer ones, we can take bonded pairs from our central atom then and create a new bond. So instead of this being a single bond now, let me do it in a different color. We're gonna have carbon again.
Good morning, my dad.
But now we're gonna take these, and this is why I say it's good to use pencil, because you'll get to this point. Oops,
Good morning.
you'll get to this point and then have to rearrange your electrons. So instead of redrawing the whole thing, you can just erase them for the purpose of having these permanently on these slides. I'm gonna take this pair of electrons. I'm going to take this pair of electrons and we're going to move them over here. And at this point, you can move them to the left side or you can move them to the right side. And actually, I think we're going to have to do both to get enough electrons. Especially, no, just one. Yeah, we're going to have to do both. Anyway, so we've taken those electrons and we moved them over. So now we have carbon with electrons here, oxygen here and here. And then we moved those in here to create another double bond, or to create another bond so we have a double bond. So now we can count these bonds contribute electrons to both oxygen and to carbon. They're shared. So oxygen then has 1, 2, 3, 4, 5, 6, 7, 8. So that oxygen is happy. Oh, sorry, these are still over here like this. But now our other oxygen is still not happy. So we're going to do the same thing. I'll switch colors here. We're going to take these electrons now, and we're going to move them into this bond. And so we'll redraw this again. So if our oxygen here, still with the double bond, carbon, now with no lone pair electrons. And then this oxygen double bonded to it as well. So now we've got 1, 2, 3, 4, 5, 6, 7, 8. That oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy. And then 1, 2, 3, 4, 5, 6, 7, 8. So each of our atoms now has 8 valence electrons. This would be the answer. So because this doesn't have, right, so this is 1, 2, 3, 4, 5, 6. Oxygen doesn't have a full set, a full octet, right, 8 electrons. So this isn't complete. Okay. Just like the stepwise way to get from, question to answer. Here, I'll circle this too. This would be the correct answer. For this next one, we're even told that HCN, which is hydrogen cyanide, has a triple bond. So we'll start again. Hydrogen, carbon.
Reverse from JCPenney, I get insurance.
Oh, interesting. In this problem, I would probably give you, I guess I would tell you where the central, I would tell you here that carbon is the central atom. Carbon is almost always a central atom. Almost always. But I would tell you in this problem, hydrogen can't be a central atom because it doesn't have enough electrons. It only forms one bond ever. Whoops. So hydrogen is 1 electron, carbon is 4, nitrogen is 5. So then we're going to write, again, I would tell you carbons are a central atom. So that means everything else is going to be bound to carbon. We're going to put hydrogen, nitrogen. Oh, sorry, I didn't count these. We're going to have a 10 total valence electrons. And then since we have 2 bonds, again, we're going to subtract out 4 bonded electrons. And this is really just this subtracting out, subtracting out the 4 like this is just when you're getting started, because obviously here we ended up with 8 total bonded electrons, 2 for each of those 4 bonds. But when you're getting started, we can subtract these ones out of our count that we're just going to start dotting in. So we're going to end up with 6 valence electrons that we're going to be filling in here. And we'll fill our central atom first. So 1, 2, 3, 4, 5, 6. You'll notice that I didn't give hydrogen any more electrons. That's because hydrogen is happy with 2. So we don't need to give it any more electrons. And that'll be the case always when you have hydrogen. Hydrogen forms 1 bond, it's done. Don't give it any more electrons. It doesn't know what to do with them. Okay, so now we can count our valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 for carbon. So that's good. But for nitrogen, 1, 2, 3, 4, oh, that's it. So what we're going to have to do then is we're going to have to move 4 more electrons from our central atom to our nitrogen in the form of 2 more bonds.
Because I'm glad
here, and we're going to move those.
But I just remembered that
a bond, another bond.
And he posts the lectures, so I don't know why I went to class.
So, oh wait, I'll keep doing blue.
Well, guess what? I freaking
If we were to redraw this, hydrogen, carbon,
No, I'm
we've
just
taken
kidding.
both of those lone pair electrons and we've moved
Just
them into
kidding.
this bond. So we've got a triple bond now. And then nitrogen,
Little.
2 lone pair electrons.
Why do you want me to?
So then this would be the answer. For for carbon. Yeah, so carbon has 8 valence electrons. So it's good. These ones are all shared. So we'll count them for nitrogen as well. I'll say 1, oops, switching to my eraser. Oh, you mean this 6? No, so this number of 6 is the number of electrons that we have to place around. So we created these 2 bonds, and then we get to place in 6 more electrons from our total pool of valence electrons. So every atom, aside from hydrogen, is going to end up with 8. Yeah, so this 6 is because we had, right, 1 from hydrogen, 4 from carbon, 5 from nitrogen, 10 valence electrons total. And so when we draw this out, we draw our carbon in, and then we have to have at least 1 bond between nitrogen and hydrogen. So we're subtracting out those 4 bonded electrons from our total pool of 10. And then we just have 6 electrons left. We placed 1, 2, 3, 4, 5, 6. Okay. Move on. And there are step-by-step instructions here. So sometimes in symmetrical molecules especially, we can get what are called resonance structures. Let's see, how much of this do I want to read? Yeah, so Lewis structures give us an idea and a way to predict also how atoms are bonded or connected in molecules. The bonds and lone pairs represent electron density. Electron density. And then when we have more than one Lewis structure possible for a single molecule, all are correct. The actual structure is more like a composite of all possible Lewis structures. So really, when we look at something like this and we have this nitrate, so we've got a double bond here, but because each of these is an oxygen, it's possible to draw this double bond here or here. So when you're given a problem, and I will let you know if there's resonance structures that I want you to draw, or, well, I guess this is going to be like, I don't know, for this class, you'll be able to actually draw stuff on the exam.
Hey,
this won't be on the next exam. It'll be on the next exam. So I will have you draw some Lewis structures, and I'll let you know if there are resonance structures that I want to see. So the real structure of this is going to be more like nitrogen bonded to each of these oxygens, and then like hybrid bonds in between them. For this class, we'll draw out all the resonance structures. And you can kind of see that this is the same thing as well, because, right, at least between this one and this one, this one and this one, if you just flip it, it's the same thing. The one is a mirror image of the other, and we can just, if we took this like a pancake and flipped it over, it would be this. And then really the way that these arrange is going to be more evenly spaced. So more than that, we can just rotate this one and get this one. So these are indistinguishable from each other, and they're all correct. So let me, yeah, all correct.
Nick.
Okay. So to put these into steps, especially for these polyatomic ions, again, do like we've been doing. You obtain the total number of valence electrons for the structure and account for the ion's charge. So here we would have 6 times 3 for each of the oxygens. And so oxygen would be 6 times 3. And we have nitrogen would be 5 times 1. And then we would have a charge. Again, if you have a negative charge, that's adding electrons to your valence pool. If you have a positive charge, you're removing electrons from your valence pool. So this is going to be an extra 1 electron. Again, the single atom in a formula is usually the central atom, or I'll let you know what it is. For this one, nitrogen. Then we make single bonds between each of the atoms, between the central atom and the outer atoms. And each of those is 2 electrons. And then we distribute the remaining valence electrons so that each atom obtains a noble gas configuration of 8 electrons, also known as an octet, except for hydrogen. And then if an atom is electron deficient, we use lone pairs from other atoms to form double bonds. And usually, if you do this extra step, right? Not just distribute, like do this. So distribute, but distribute evenly. So if you distribute them evenly to the outer atoms, filling the central atom first, then you'll just have to be taking electrons from your central atom to make those double bonds. And then you draw, sometimes triple bonds are needed. And then you draw all possible Lewis structures. That's maybe the trickiest part, but I'll try to let you know when there are going to be other structures, so you know to look for them. The correct answer that I would look for on an exam or something would be to have all 3. Yeah. Each of these. Yeah. So I'll tell you that there are resonance structures, but then, I expect you to draw all the resonance structures, which are really just move this double bond around to each of the outer atoms or to anywhere that it could be. All right, so let's do another example here. We'll draw the Lewis structure for carbonate. So if carbon and oxygen. So carbon's going to be 4 valence electrons, oxygen is 6. And then we have 3 oxygens. Multiply that by 3. We also have a charge. Our charge here is a -2. Right? So whenever we have a negative charge, we add electrons. We're going to add 2 more electrons for
when
that
you
charge.
check, let me know. That way, because remember I told you you use you to pick up
6 times 3 is 18. Plus 2 is 20.
Yeah, that's right.
24.
Why did you just tell me?
That's our total electron pool.
Like, when do you need me?
I'll go over here and we have
Why do I need
our
you
central
to
atom's usually going to be the single one. So we'll have carbon.
Because the girl is in Selena.
And then we're going to draw in our bonds, our oxygen atoms.
She sells these skincare shit, whatever. Like a little.
So now this is where we've taken some electrons out of our electron pool by creating these single bonds. So we made 3 single bonds. it's going to be 6 electrons. So then we have 18 electrons
I think it's gonna be cool.
place.
But like it's probably not gonna come out.
We'll go 1, 2, 3,
It's gonna be
4,
70 but cloudy.
5, 6,
Eat
7,
my ass.
8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
I was like, no, I put lotion on my own.
You are.
Oh, it actually ended up weird.
You mean ashy?
So if you get lone pair electrons, if you get single electrons like this, 1 electron on each, you can bring those together to make a pair on one of them.
You're perfect. Just
So I'm going to take this electron and I'm going to move him up here. So he ends up as a pair. Delete him, put him up here.
Oh my god. Dude, that's what happened to me when I had my nails. They waited. I literally worked 1 to 9 that day and they sent me home.
Okay,
at
so
freaking 8.
now we would count the number of electrons that each of these atoms has.
Yeah, they didn't
So
even notice the whole time. I was
oxygen-
wearing gloves. I think
Oxygen has
I think
8.
someone from
This
back
oxygen has 8.
some. I was like, no.
This has got 2 from the lone pair and then 6 around it. This oxygen also has 8. 2 from the bond. I think I said lone pair there, but 2 from the bond.
Yeah, I was like,
And
yeah,
then
whatever.
6
At least
lone
I
pair electrons around
didn't
it.
come in for just an hour.
Carbon's got 3 bonds, so that's 6 electrons, plus these 2 is 8. But our last oxygen
Yeah,
only
so
has,
you
right,
gotta
2,
go to
4,
gym even though you took forever
6.
and you only went there for like 30
But
minutes.
we can take our electrons or extra lone pair from carbon, and it will so generously lend them to this oxygen. So, all right, we're going to take these and we're going to move them over here. So I will redraw this. You don't have to redraw this if you want, and I will upload these slides.
Should have done hip thrust. Wait, is that on there? I don't think it is.
Like that,
I like box
if
squats.
not a little sloppy.
Me.
Okay. Now, though, we have symmetry around this molecule. All right, so this oxygen, if we took this and we spun it, wouldn't be able to distinguish between this oxygen if it landed in this position or if it landed in this position. So we can draw resonance structures for this. And really all that you're doing is you're going to take that double bond, and you're going to move it to one of the other oxygens until it's been at every position. So I'm just going to move it from here to here. That's going to change the number of electrons around the oxygen as well, right? So we're just taking this and essentially rotating it. Actually, sorry, this needs 2 minus. All right, so we have a charge. We need to represent that charge with brackets
You scare me.
to say that this whole thing,
I'm getting a cramp in my leg.
charge of 2 minus.
Yeah, you scared me.
And then our
You're a
final
scary
resonance
person.
structure will be,
You're a scary person. Look at your
I just
face.
realized I should have done this.
I thought we said we weren't ever gonna speak on that.
Oh, I could do this. Right, so basically we're taking
F
this,
to the U.
now it's up here.
Mm.
And so we're gonna draw it one more time.
That's so
Yes, going to the right.
Fuck you. You're such an a-hole.
It's-
unbelievable.
It's more of an understanding check here.
Unbelievable.
Yeah.
Unfucking believable.
Unbelievable.
I'm making you do it just to like check understanding.
Oh.
Yeah.
Okay.
That's kind of hot.
So some of these, yeah, so that's how you draw those resonance structures. And yeah, you're just sort of rotating that around, showing that it could be in any of those positions and that they're all equivalent. Says some molecules, but I think a lot of molecules don't have resonance structures. There's only one way to draw them. So let me zoom in on this table here a little bit. So if we look at something like chlorine, that looks a lot like other ones that we were drawing before. There's only one way to draw that. You can't draw it a different way. This hydrochloric acid would not have a resonance structure. You could draw this hydrogen, on the right side instead, or on the top, or on the bottom, or really at any angle in between. But it's still, well, I guess resonance structures are still essentially the same thing. But it's always going to be a double bond or a triple bond that moves in a resonance structure. So like this, you have a double bond, could be on either oxygen. So that has a resonance structure. But if you fill in all of your electrons and you don't end up with any double bonds and everything has an octet, you're not going to have a resonance structure. It's just these double bonds that can be in different places that create resonance structures.
I'm hungry.
Oh, and this actually lays out too. So this is exactly what we're doing, right? So this is
a fly swatter
2 times 7. We have 2 chlorines times 7 valence electrons. That gives us 14. We build a single bond. So we're subtracting those 2 electrons from our pool of possible valence electrons because we used them. Because we have to use them. So that gives us 12 remaining electrons to place around our atoms.
I do use it, you fucking pussy.
No, you don't. Because you're scared of flies.
I think I'm scared of
Any questions there?
That is the most rude thing you've ever said to me.
All right, so that's how we draw these valence. That's how we use these valence electrons to predict structures. Now, Vesper theory, or valence shell electron pair repulsion theory. It's really Vesper, but I like saying Vesper because it's a lot easier to say. So this Vesper theory is used to predict 3-dimensional structures of molecules.
Yeah, right.
Because these molecules don't exist flat on pieces of paper. They occupy 3-dimensional space. So this theory is that the electrons in a covalent bond repel other covalent bonds. And the bond angles between all covalent bonds in the molecule are as far apart as possible. Oh, shoot, I should have grabbed that model.
Because then you're all cranky driving to work because there's traffic.
There's a really cool website that has a bunch of molecules on it that you can go and you can click on them and then click on it with your mouse and drag it around and see the 3D shapes.
I had to wait like 10 minutes for you.
Oh, perfect. Yeah, so I'll find, if you can find it on there for 3-dimensional models. There are also just YouTube videos of the models rotating. And I'm sure there are apps as well. So anyways, the idea is that these electron pairs and these bonds represent negative charges, right? And similar charges repel each other.
Okay, I'm gonna tell the girl.
So they're gonna repel each other to be as far apart as possible. So it's something like, well, when we have 2 double bonds, like on CO2 here, which we did earlier.
Because you're only a coach in the morning.
These bonds
the rest of the day off.
Are going to create this linear shape by being as far apart as possible. Right? There's nowhere that they can move. You can move it this way. It's a little bit closer on one angle. You move this. I mean, they stay far apart. The way that you can do this, I mean, we're going to get into it. Is just by looking at the central atom.
Why you up to sexual?
We're always doing this based on the central atom. And then counting the number of bonded pairs and lone pairs around that central
I
atom.
was trying to trick my head.
We'll see that. Okay, so right, so with 2 electron groups, we have 2
Dude,
bonded
you
electron
my
groups.
hair.
At Chick-fil-A?
Then we're going to be linear.
Tell them I'm gonna beat
2
them
electron groups in
in front of
general
your hair.
will just be linear.
Yeah. That's so rude. Tell them I think it looks great.
If you have 3 electron groups, then you have 2 different
said that?
possibilities.
My bae, did she tell you?
You can be either trigonal planar.
My bae better not make fun of me.
So this is
Actually,
3
maybe I'll let
bonded
one thing
groups.
slide. But that's it.
The fuck? You shouldn't let anything slide.
Yeah, but you make fun of my bae too, so.
Which is trigonal planar. And then for this bent shape, we have 3 electron groups again, but one of those is a lone pair. So lone pairs, we don't count as a part of our geometry. They don't have mass, they don't take up space. They're just a sort of ambiguous cloud of negative charge. But they force the other 2 groups to get far away from it as well. So if you look at, zoom on this again. So if we look at this carbon atom, it just has these, like the hydrogen, the oxygen. So when those are spread out as far as possible, that's like, well, it's the inverted of this, it's the Y from the YMCA. And so you get this trigonal, tri being 3, planar, it's also flat because that's as far apart as they can get. This bent shape, there's an electron cloud here, doesn't have mass, but forces the oxygens on the sulfur dioxide to move away from it. So then the shape that the atoms make, not the electron clouds, is bent. So this slide only talks about electron groups, but you can also think of these as you have 3 electron groups. And in this one, we have 3 bonding groups and 0 lone pairs.
Because I've been taking my birth control on time.
For bent shape, we have, again, 3 electron groups.
Yeah.
The difference is we only have 2 bonding groups. And 1 lone pair.
Then do it.
Oh, and I guess I should address this too, so it doesn't cause confusion later. There's our,
Oh my God.
doesn't label it this. This is the molecular geometry.
You're the one
this one, this one.
First of all.
We also have,
Very disrespectful to your elders. Okay.
yeah.
Hey, shut the
So
fuck
this
up.
is electron group geometry.
You're fucking 19.
Electron group geometry.
You're not even 20. So shut up.
Tell me
I
why.
don't remember if there's a table. You can find tables though that break these up into electron lone pairs, bonding groups, and then sorts it out that way.
I have breast cancer.
Okay. We'll see more examples too.
Cancer.
So if we have a central atom with 4 electron groups, again, we have a difference between our
I love you more than anything.
electron group geometry. That makes it really hard to read. Our electron group geometry. And then this again is our molecular
July.
geometry.
So we've been together since July.
But here, because we have, again, 4
That's fucking bullshit.
electron groups,
No, it's because I have boob cancer. I'm sorry.
how many bonding groups do we have? 4. Right, each of these has a hydrogen on the end. So we have 4 bonding groups. How many lone pairs do we have? None. 0 lone pairs. So that's sort of the identity of the tetrahedral, bless you, is that we have 4 electron groups, and all 4 of those electron groups are bonding groups. Gives you a tetrahedral shape.
He doesn't care that you know that.
I don't give a shit.
Shut up, bitch. Who said you could talk?
So we come down then and look at this
Oh, I said
next
no.
molecule, which is ammonia.
Ooh.
We have, again, 4 electron groups.
Damn, it looks hella ugly.
But now how many bonding groups do we have?
Yeah, because it is.
3 bonding groups. There's only 3, and you can just count the atoms that are attached to it. 3 electron groups.
75.
Sorry. Bonding groups.
And tomorrow it's going to be 80 here. Bro, it's literally fall. Why is it 80?
How many lone pairs do we have?
What
We have
the
1
fuck?
lone pair.
So what time are you off? 6 again?
So our number of bonding groups
Yes.
and our number of
I am.
lone pairs will equal, yeah, it's over here. But you can also sort of just deduce it from the fact that we have 4 electron groups. Well, I guess you'd have to know from the Lewis structure, you would know that there's 4 electron groups. And then you could say there's 3 bonding groups because we have 3 atoms attached. So then there must be 1 lone pair.
7
And that
plus
gives us
1, 8.
Huh?
7 plus 1,
trigonal
8. You're up at 8?
It says minus 1, you idiot.
for middle. Right. It's a little tripod.
All right, we're getting to that point though.
No.
Love you.
No. I love you more, Jackson.
And then as we add more electron groups, we can add more different shapes. So this is a slightly different bent shape. It's the bent shape. It's still just called bent. But it's the bent that you get when you have still, again, 4 electron groups.
What if I actually died?
But now we only have 2 bonding groups.
What if I died? What if I died?
We have 2 lone pairs. So you get a similar shape, not exactly the same as our previous bent shape.
Everybody.
For the terms of this class, I'm calling it the same thing. The angle between there is smaller,
What if I
but it's still just a bent shape.
just dropped it?
Yeah. So this is one of those good flashcard candidates where you put the number of electron groups, bonding pairs, or bonding groups and lone pairs on one side, and then the name of the shape. And you can do again, there's our electron group geometry, which is only dependent on the number of electron groups that we have. So even though this is a trigonal pyramidal molecular shape, molecular geometry, it's also a tetrahedral electron group geometry, simply because it has 4 electron groups. So everything with 4 electron groups can be tetrahedral electron group geometry, but can have different molecular geometries. So again, oh yeah, good. There's a table in the book. This would be the table to look at to make those flashcards, because you have your electron groups, you have your bonded atoms, you have your lone pairs. I'm not going to ask you about angles, but you also have your molecular shape and your electron group geometry. So this could also be molecular geometry. Yeah. All right, so the theory here just being that they're spreading apart as far as possible. It can help to have really a good mental image of what those look like and how things spread out. If you want to go to like Michael's or a craft store and get those like styrofoamy balls and like some toothpicks or something, then you can play with making these shapes. And you'll see that when you put one toothpick in, you say, okay, I want to put another toothpick in as far apart as possible. You would get this linear shape, right? Because the farthest part away is on the other side. But if you have 2 or 3 things in there, you put one in, say, well, I'm going to put another one in, but I'm going to have to put a second one in and spread them out as far as possible. And you're going to end up with, well, trigonal planar. When you add 4 things on there, that's the hardest to, I think even when you're holding it in your hands, it's the hardest to conceptualize because they have to be spread out sort of at these odd angles. It's actually 109 degrees is the angle between them. But that would be an exercise I'd recommend. So a very useful table there. I think we're going to stop there and pick up with this again next week because it's 9:45. And then study up on those shapes because those shapes are going to help a lot when we start talking about electronegativity and polarity. Because anything that's not symmetrical is going to be polar. All right. I'll end the recording.